In this video, we are going to continue the quantum size effect on the physical properties of the nanomaterial. The quantum size effect is the most pronounced for semiconductor nanoparticles, where the band gap increases with a decreasing the size. When you are decreasing the size, the band gap will be increases. That means the energy level will be increased for the particular nanomaterial, resulting the interbond transition shifting to the higher frequency. In a semiconductor, the energy separation, that is the energy difference between the completely filled valence bond and the empty conduction bond is harder, a few electrovolt, and increasing rapidly with decreasing the size. Then the mechanical properties. Mechanical properties of nanoparticles deals with bulk metallic and ceramic materials, influence of porosity, influence of grain sizes, superplasticity, filled in polymer composites, particle filled polymers, polymer based nanocomposites, filled with pellets, carbon nanotubes based on the composites. So the mechanical properties are based on these things. Then the discussion of mechanical properties of nanoparticles is some extent to only of quite basic interest. The reason being that is the problematic to produce the macroscopic bodies with high density and grain size is larger, not in the range less than the 100 nanometers. However, two materials, neither of which is produced by pressing and sintering, have attracted much greater interest as they will undoubtedly achieve industrial importance. So based on these two processes, we can achieve the better mechanical property, better particles as compared to the conventional material. These materials are polymer which contains nanoparticles or nanotubes to improve their mechanical behavior, and severely plastic deformed metals which exhibits the atomising better properties. However, because of their large grain size, the latter are generally not accepted as a nanomaterial, because the only small particles also are only accepted as a nanoparticle. Experimental studies on the mechanical properties of bulk materials are generally impaired by major experimental problems in producing specimens which exactly defined grain size, a small size, and porosities also. Therefore, the model calculations and molecular dynamic studies are major importance for understanding of the mechanical properties of this material. Filling polymers with nanoparticles or nanorods and nanotubes respectively leads to significantly improvements in their mechanical property. Such improvements depends heavily on the type of filler and way in which their filling conducted. What type of filler we are using, then how we are filling. The experimental setup also very important for improvement the mechanical property. The latter point is a special important, as any specific advantage of the nanoparticulate filler may be lost if the filler forms aggregates. There may be mimicking the larger particle that will be converted as created as a larger particle. So due to that, what happens, the mechanical property will be decreased. Next, the particulate filled polymer based nanocomposites exhibit a broad range of failure, strength, and strains. So this depends on the shape of the filler. Particles are pellets, and the degrees of agglomerations. Next, in this class of material, polymers filled with silicate pellets exhibits the best mechanical properties and are the greatest economic relevance. The larger of the particles of the filler and agglomerates, the poorer are the properties obtained. The poorer we will obtained because of the above things. Although the potentially the best composites are those filled with the nanofibers or nanotubes, experience experience. Sometimes composites have least ductility will be getting. On the other hand, by using carbon nanotubes, it is the possible to produce composites fibers with extremely high strength and strain at rupture conditions. Among the most exciting nanocomposites are the polymer ceramic nanocomposites, where the ceramic faces the palletlet shaped. This type of composites preferred in nature and is found in the structure of bones, where it is consists of crystallized minerals pellets of a few nanometers thickness that are bound together with collagen as the matrix. So composites consisting of a polymer matrix and defoliated physio oscillates exhibits excellent mechanical and thermal properties. Bulk gold and PT are the non-magnetic, but at the nano size they are magnetic. Surface atoms are not only different to bulk atoms, but they can also modified by. Then this type of composites is preferred in nature and is found in the structure of bones, where it is consists of the crystallized minerals pellets of a few nanometer thickness that are bound together with collagen as the matrix. Composites consisting of a polymer matrix and defoliated physio oscillates exhibits excellent mechanical and thermal properties. Then bulk gold and PT are the non-magnetics when it is the normal condition, that is bulk material, like a bulk material, but in the nano size they are the magnetic. Surface atoms are not only different to bulk material atoms, but they can also be modified by interaction with other chemical species, that is by capping the nanoparticles. This phenomenon opens the possibility to modify the physical properties of the nanoparticles by capping them with the appropriate molecules. Actually, it should be possible that non-ferromagnetic bulk material exhibits ferromagnetic-like behavior when prepared as a nano range. That is, when you are reducing as a size, we will get the nano range. So, bulk material reducing as the nano range, so it will be behave like a magnetic ferromagnetic. One can obtain magnetic nanoparticle of PD and PT, and then a surprising case of the AU, that is diamagnetic in bulk formation from non-magnetic bulk materials. In this case of PT and PD, the ferromagnetism arises from the structure changes associated with the size effects. Here you can see this super paramagnetic condition. Okay, then it will be given as a single domain. We will given as then it is a multiple domain. They will be curved. You will get the magnetic properties of the nanostructure. Okay, they will given as the magnetic properties of the super magnetic structure. Okay, and then it is decreasing. It will be increasing the diameter size. Okay, so when its diameter size is decreased, it will be given as a at a particular size it will be given as a better magnetic paramagnetic. Okay. Then, however, the gold nanoparticle becomes the ferromagnetic when they are capped with the appropriate molecules. They charge localized at the particle's surface gives rise to ferromagnetic like behavior. Surface and the core of AU nanoparticles with 2 nanometer in diameter shows the ferromagnetic and paramagnetic both characteristics respectively. The large spin orbit coupling of these noble metals can yield the large anisotropic and therefore exhibit the high ordering temperatures. More surprisingly, permanent magnetism was observed up to the room temperature for thiol capped gold nanoparticle. For nanoparticles with sizes below 2 nanometer with localized carrier are in the band 5 diameter band, bulk gold has an extremely low density of states and becomes diamagnetic. So, as is also the case for bare gold nanoparticles. These observations suggested that the modification of the D band structure by chemical bonding can induce ferromagnetics like character in metallic cluster. Next, we are going to see the carbon nanotube emitters. Carbon fibers typically 7 pm, that means parts per minute in diameter, have been used as electron emitters. However, they suffer from poor reproducibility and rapid deterioration in the temperature of 130 in the typical 137. Then carbon nanotubes have high aspect ratio and small radius of curvature. In addition, their excellent chemical stability and mechanical strength are the advantages for the application in the field emitters. That is a very important point. Then Rezeles et demonstrated the laser irradiation and the induced electron field emission from the individual multi-wall nanotube. Although the emission current of the single tube is constrained because of its very small dimension. An array of nanotube oriented perpendicular to an electrode would make an efficient field emitter. Here it will showing the CRT lighting element equipped with the aligned with the carbon nanotubes emitter on SUS 304. So A is indicating the operating device, P is the structure. So the electron tube is 20 mm in diameter and 75 mm long. So carbon a flat panel display based on the nanotube field emission was also demonstrated. A 32 into 32 matrix addressable diode nanotube displayed prototype was fabricated and a steady emission was produced in the vacuum. Then pixels were well defined and switchable under a all voltage of pixel scheme. A fully sealed field of emission display of 4.5 inch in size of has been fabricated using a single walled carbon nanotube organic binder. This is the single walled carbon nanotube binder. Then a nanotube were vertically aligned using phase squeeze and surface submarine techniques, and fabricated displays were fully scalable at a temperature as low as 41.5 degrees Celsius. The turn on the field of 1 volume per meter and brightness of 1800 at 3.7 was V per pm was observed on the entire 4.5 inch area from the green phosphor indium tin oxide glass. So the figure shows the CRT lighting element equipped with aligned CNT emitter, and the electron tube is 20 mm diameter and 75 mm long. So the test of this cathode ray tube lighting emitter suggested the lifetime of exceeding 10,000 hours. So that is the very important point, and application of the carbon nanotube emitter. So thank you for watching this video.